Okay, so load line analysis example of a common emitter amplifier. Two more points on what happens when V in of t exceeds the value on either the positive or the negative side. And if you remember the modes of operation, right? We have cutoff, we have saturation, we have active. We bias the transistor such that it performs, or it should perform in the active region. But depending on the value of V in, it could drive the transistor either to cutoff or to saturation also, because V in of t is going positive as well as negative, right? And so the example would be here. Let's see. The example would be if V in of t exceeds the limit of operation of the DC bias. Okay, limits the operation of the DC bias and the transistor. This is just the results. Basically, you're applying a input signal plus 0.4 minus 0.4, and you obtain VCE max 7 and 3. I typically don't like these kind of images because what's the first thing you see? The input seems larger than the output, which is the exact opposite of what it should be. So as a engineer, you should, picture is always worth 1,000 words. As an engineer, you should always remember that, right? This seems bigger than this. Where in fact, if you don't pay attention to the millivolts or the volts, it's the exact opposite. Anyway, this is just a summary of what the example that we just did. But as I was talking about the distortion, or the driving the transistor into saturation and cutoff, example is here. If you apply, so standard input was plus minus 0.4 volts, and we obtained the output that went from 3 to 7, right? 3 to 7 volts. Now, what if our input was much larger than 0.4? If our input was much larger than 0.4, then the amplified signal would drive the transistor into the extremes of its limits. And the limits are basically here, 0 and 10 volts. That is the VCC value we have applied. That is the VCC value we applied, right? And this is, of course, a simplistic example of what happens when you apply a large input to an amplifier circuit. Okay. Here, at the positive peaks, the transistor is being driven into saturation. And here, at the negative peaks, the transistor is being driven into cutoff. So even though we are biasing the transistor to work in the active region, it could potentially be driven into cutoff and saturation. As an example, let me show you here. If you had perhaps a large input like this, again, that's the standard input. But if you had a large input like this, then you're exceeding where exceeding the limits of the applied VCC voltage. Okay, so your Q point is now being driven way far above, beyond the biasing limits, and that drives the transistor into cutoff and saturation. The cutoff is not quite clear. It's still not beyond 10 volts, but hopefully you get the idea of what I'm trying to say. Large enough input, the transistor reaches the extremes at both points. And this, if this is your input and your output is like this, what is happening? It's chopping the top and the bottom of those signals. It's clipping. In real amplifier terms, we call this as distortion. Distortion, which you would have experienced at least once in your life. You increase the volume so high and you hear tearing sounds coming from your speakers. Anyone ever experienced that? That is distortion. Because you're cranking it up so much that you're driving the amplifiers or your audio signals into clipping at extreme ends, and so now you have distortion. And obviously, real life electronic devices have built-in protections to not do that. So you won't go beyond a certain limit. But of course, it does happen every so often. So even if you bias the transistor to work in the active region, if you apply a large enough signal, it could drive the transistor into cutoff and saturation. So designing an amplifier or designing a transistor circuit to work within that active region is part of amplifier design. Okay, it's a course that E majors take, following up in the third level, 300 level classes. So E students first take this fundamentals of semiconductor devices, then they learn about analog circuits, then digital circuits, and they combine both of those together in electronic design called mixed signal electronics, where where they learn about how to design it to work within that active region. Okay, so a couple of limitations. The first and the biggest one is, of course, that if the transistor changes, even for the same, let's go to this input right here, not that, this one. So here we have a value for beta, which is 100, right? That value is part of the spec sheet provided by the manufacturer. But it is impossible to fabricate two devices with exactly the same value of beta. You can manufacture the same transistor, same time, same temperature, same machine, everything's the same. It's just not possible to get the exact same beta values. So there's a range of beta values provided by the transistor, even if you have the exact same model. Okay, so the beta values might be from 100 to 5, not 500, but there'll be a certain range, 200 to 300, or 150 to 250, so on and so forth. Typically, if you pick two transistors from the same model family, might be some variation, not a whole lot. But let's say you take the exact same transistor as we have here. Right now, the beta value is 100. The other transistor has a beta value of 200. What would happen? Your Q point would now shift. And when it shifts, it could drive the transistor into saturation at one end, or it could drive it into cutoff. The exact same circuit with the exact same DC biasing voltages would not work exactly the same for different transistors. And that is the biggest drawback of this circuit. Okay. Right now, we can get this to work because we are saying our Q point is fixed right here. If you apply 25 microamps input, then we would obtain 25 milliamps at the output, meaning the transistor curves are telling us that the beta value for this transistor is 100. If it was 200, then for applied 25 microamps, our output would now be, what would it be? 50. So it would be somewhere over here. Different transistor, your Q point or center point is like right here. It's automatically, even before you do anything, V in, you just apply a little bit of positive V in, it's like in saturation. Does that make sense? If the beta value is below 100, then your Q point would be somewhere down here. and then again it's driving into cutoff. In both cases, it basically means the exact same thing. You cannot use the circuit for the exact same transistor. It just would not work. The second limitation is there are two different power supplies in here. We could simulate this in a lab, but it would not be possible to do so in real life without two power supplies in the same box, which again is a big limitation. We typically only have one power supply. And so circuit designers will take one power supply and then divide it up into multiple different pathways. And so from there, the solution was to obtain a different biasing circuit known as a 4-resistor bias. And this is more commonly also known as voltage divider bias. Voltage divider bias. You apply one voltage, that voltage suffices for all. So before I go to the next slide, see what's happening here. You're applying plus VCC at this point, and because it's the same node, you're applying VCC to R1 and R2 also. Does everyone see that? And then if you want to analyze this circuit, we do the same thing. We separate out the input and the output. So here, this is my input. This is my output. And that's what we obtain. This is the equivalent circuit when we divide it into two parts. Input side and the output side. Both sides are powered by the same exact voltage source, but we can obtain a secondary voltage depending on the values of R1 and R2. You have a voltage, DC voltage applied to a series combination of resistors voltage in a series combination of resistors or components gets divided, hence the name voltage divider bias. Current flows through this pathway, so the voltage is plus minus, and then this point is going into the base emitter junction. Right? That point of the voltage divider bias is going into the base. That's where you're applying the input. So let's take a pause, think over all of that. Let me know if you have any questions. Make sense? We could, of course, have as many resistors as we want to create even more voltage outputs, which is what happens in our laptops or any other device for that matter, right? If you take a laptop as an example, requires different voltage for your processing, CPU, graphics processors, memory chips, USB ports, hard drives, they all require different voltages. But you only have one voltage going into your laptop, which is 18 volts, typically 18 or 19 volts. That 18 or 19 volts is then split using circuits similar to this. You have voltage dividers, you have Zener diodes, voltage regulators that would give you one specific output for different parts of your system. If you have ever looked at a desktop, at the back, you have these power supplies. And inside, you would see a thick cable. That cable is basically comprised of about 15 to 20 wires, and they all go into the main board. And so it's different voltages coming from that power supply. Anyway, coming back to our circuit. So we have this circuit going into our input side, okay? And here's what do we do with this? Thevenin equivalent circuit. If you have taken 201 with me, you know how I keep on harping that Thevenin and Norton are very important to circuit analysis. And you can see it'll keep showing up over and over again. So we need to find the voltage that is going into the base. And how do we do that? We find the Thevenin circuit, meaning Thevenin voltage, and the equivalent resistance that is seen by the base. So you find the Thevenin equivalent circuit as seen by the base emitter junction of that transistor. Okay, as seen by the base. So that circuit devolves to something like this. You have a voltage, you have a resistance going in, and this is, of course, going into the base emitter junction. I'll call this VTH. That VTH would be the base voltage, right? And this would be RTH. That RTH is, of course, the base resistance. So the circuit comes out to be equivalent to the one that we studied just in the previous example. Okay. The only thing is that because of one voltage supply, we're using two physical resistors to create that equivalent RB. And in this case, VB is simply given by voltage division. It'd be VCC times R2 over R1 plus R2. Okay, R2 over R1 plus R2. And then, of course, RTH or REQ, you would short out the power supply, and you would get R1 in parallel with R2 as seen by the base. So this means it is the product of R1, R2 divided by R1 plus R2. Okay. Nothing that is really new in this sense. This is from 201. The only thing we are doing is we are using single power supply to create two different ones. Okay, and from that point on, of course, we would simply proceed with the analysis as we did for the previous example. The only difference would be that we have one single power supply. Okay, so remember how I said we have multiple different models depending on, multiple different models for diodes, multiple different models for a BJT, depending on the application and depending on the surrounding, the surrounding circuitry. So here is one of those models. Typically, a bipolar junction transistor is modeled as a current source. It is modeled as a dependent current source that provides a gain for the input current. Your input current is IB, output is IC. IC is beta times IB. So we model the transistor as a dependent current source, and the dependent current source provides a current that is dependent on the value of IB. If you remember 201, I talked about dependent and independent current voltage and current sources in chapter 1. And this is one of those models. Okay, so if we do that, we are still analyzing the same circuit as that previous example. We're just using a different kind of model. Okay, we're just using a different kind of model. So in this model, we can say that we're applying a voltage at the base, we are applying a voltage at the collector. We have the same base resistor RB, same collector resistor RC. We now have an extra resistor RE, which we didn't have in this circuit. Right? We didn't have a RE in this circuit. We have an RE in the next voltage divider circuit. And so while the circuit looks pretty much the same, there is an extra resistor, and hence the name also 4 resistor bias. 4 resistor bias. Okay. Analysis techniques can proceed in the exact same manner. We can apply KVL, we can apply KCL, we can apply Ohm's law to determine what our output would be. So let's say we have a, okay, hold on. Let's say we have a transistor, we connect 4 resistors to it, RC, RE, R1, and R2. If you wish to begin analysis of this, first we determine the Thevenin equivalent circuit for the input side. Then we apply KVL, determine our expressions for VBE and IB, and then we apply KVL on the output side. Okay, so if you look at this model, we can see that there will be voltage drops across these resistors with the polarity as shown. Okay. So if you apply KVL on the input side, we have 4 voltages. We have VB, VRB, VBE, and RE. So let me write that down. VB, the base voltage, then VRB, voltage across the RB resistor, VBE, and VRE. VB is minus, VRB is plus, VBE is also plus, and VRE is also plus. That comes up to 0. If we substitute okay, this I hadn't covered. We had equations for IE, IB, and IC. The relationships between IB and IC is given by beta, right? So IC is beta times IB. IE from KCL was IB plus IC, right? The total emitter current is the base current plus the collector current. From those equations, we can write that IE, the emitter current, is beta plus 1 times IB. Okay, beta plus 1 times IB. This is simply beta times IB gives you IC, and IB times 1 gives you IB. So it's IC plus IB. That's all it is. So we plug that into the above expression. What do we get? We get VB minus VBE equals IB RB plus beta plus 1 times IB times RE. Okay. 1137. Okay. And so if we solve this and we get IB outside, we get VB minus VBE, and IB is outside. We got RB plus beta plus 1 times RE. And we obtain an expression for IB as VB minus VBE divided by RB plus beta plus 1 RE. And that is the expression for the input current. Same standard approach. Okay, we just have a model, different biasing circuit, but we apply KVL to the input side and we solve to obtain an equation for IB. Okay, so let's take a pause. Let me know if you have any questions. All right, any questions? The steps make sense? Okay. All right, output KVL is straightforward. We have so the output, we want to find the voltage across the collector and the emitter, right? So we'd say collector is plus, emitter is minus. So we'd have voltages VRE, VCE, then VRC, and VCC is equal to 0. Based on our assumed current directions, we would have minus VRE minus VCE minus VRC plus VCC is equal to 0. Our output is the collector to emitter voltage. So our goal is to obtain an equation for VCE. So VCE would be given by VCC minus ICRC minus IE RE. Okay, IE RE. No, sorry. Let's look at the problem statement. Make sense on the output side? Okay. All right, problem statement for the example. So we have an example where the values for the resistors are given. VCC is given to us. We are asked to find the output voltage. And let's see, that's the last one. Okay. Okay, so determine output if the beta for the circuit, sorry, not circuit, the beta for the transistor is 100, and if you use a different transistor with a beta of 300. Okay, the assumption is because it's an amplifier working in the active region, then the VBE should be equal to 0.7 volts. So this is the information given to us plus the values given in the circuit diagram. Okay. So what do we do first? Well, first we find a value for RB. What do you mean by output? Anyone? If you read this problem statement, says determine the output, what is it asking you to do? Output voltage, yes, output voltage and output current. So it's on the collector side. So it's VCE and also IC. Input side is VB and IB. Output is IC and VCE. So if it says determine the output voltage, then it will be VCE. If it just says determine output, then we don't really know what it's asking for. Then you find everything. Okay, just a small tip. So as an engineer, if you're just asked, hey, here's a system, what's the output for the system? Well, then you find everything that appears in the output in that system, even power if you need. Anyway, so here says determine the output. Output means you find the collector current and the collector voltage. Okay, so using the analysis that we just performed, we first find RB. We determine the equation, so all we are going to do is plug in the values. RB is R1 times R2 divided by R1 plus R2. Plug in the two values from there in the equation. You obtain RB as not kilo ohms, ohms. So typically when you have values like these, I don't like to use unit prefixes. Okay, if you use 3.3 kilo ohms versus 3,333.33 ohms, it's going to give you a slightly different answer. Okay, if you do 3.3 kilo ohms or 3.33 kilo ohms, your value is going to be 3330 versus if I do this, then my value is 3333.33. So a difference of 3 ohms would sometimes make a big difference. Okay, so just another small tip. Okay, and then VB, of course, from the voltage division, I have VCC is 15 volts times 5 kilo ohms. So let me just write down the equation. VCC times R2 over R1 plus R2. Plug in the values. And this is straightforward, obtain 5 volts. Now I have to find IB for two different transistors, where the beta value is 100 and the beta value is 300. So if beta is 100, my IB from the standard equation is 5 VB minus VBE is 5 minus 0.7 divided by my RB 333 plus beta plus 1, so 100 plus 1 times RE 1000. Right? You get my equation correct? Yes, beta plus 1 times RE, so 100 plus 1 times 1000. And I obtain 41.2 microamps. 41.2 microamps. Do the same thing for beta is equal to 300. And you obtain an IB value of 14.1 microamps. So think about how the circuit has changed. Actually, not the circuit, the analysis has changed due to the same transistor, same model transistor, but a different value of beta. Your IB is now 41.2 microamps versus 14.1 microamps. Do you all see that? But now let's look at what happens to IC, my output current. Output current IC is beta times IB. So for beta is equal to 100, my IC is 4.12 milliamps. And for beta is equal to 300, it's only 3 times. So IC is 4.24 milliamps. And this is the main point. There is not much of a difference. Even though the beta is 3 times as much as the first one, the collector current has not changed much. So your bias point of the transistor is fixed in the middle. Doesn't matter what V in you give. Okay. And that's the most important takeaway from this circuit. The bias point, the Q point, the operating point does not move much for any variation in beta, meaning you can use any transistor from that model family and plug it into the circuit, and the same circuit will work just fine. And the most important takeaway. Lastly, if you wanted to find VCE, you would simply plug in the values of IC into that equation. And so VCE would be equal to VCC minus IC times 1 minus 4.16 times 1. Okay, that gives you a voltage of 6.72 volts. .16 times 1. beta is equal to 300. VCE is VCC minus IC, which is 4.24 times 1000 ohms. This is, let me explain. This is milliamps and this is kilo ohms. So I just took it out. 10 raised to minus 3 and 10 raised to plus 3. That's what I did for all of them. And here my IE would be 4.24 plus IB 14.14. So it gives me 4.25 milliamps times 1000 ohms. 4.25 times 1 gives me 6.5 volts, 6.51. And again, not much variation, not much difference in values. Okay. The main point is beta variation does not affect output. It does not affect output. Yes. That's IE. So here, let's go back. And so that's IE, the emitter current. In the emitter current, that's a good question. Let me just write it out right here. IE is IC plus, let's do it this way. IE is IC plus IB. And so for beta is equal to 100, IE is 4.12 milliamps plus, what is it for 100? 41.2 microamps. And this is for beta is equal to 100. Beta is equal to 300. IE is 4.24 milliamps plus IB is 14.1 microamps. That's where these values come from. This comes out to be 4.16. This comes out to be 4.25. Okay, questions? I want to summarize, okay? You had a BJT. We applied DC voltages to that BJT, 3 sides, collector, base, emitter. The application of the DC voltages is known as biasing. Biasing means you're creating a baseline of operation for your transistor. You're telling the transistor, I want you to work at this spot on the load line, okay? When we analyze the circuit, we divide it into 2 parts. One side is the input, the other side is the output. On the input side, we apply KVL. On the output side also, we apply KVL. Both sides, when you apply KVL, you obtain an expression. On the input side, we have the input base current and the input base current and the input base voltage. On the output side, we have the output collector current and the output collector voltage. The first circuit we looked at was simple common emitter amplifier with a resistor at the collector and at the base. There was no emitter resistor, but it required 2 power supplies, VBB and VCC, which is not practical in real life. Okay, so that's the most basic configuration. Then we applied KVL on both sides. We obtained expressions for IB, and at the output side, we obtained expressions for VCE and IC. It's not practical in the sense that if you take a transistor out from that circuit and you plug in the exact same transistor, like a different transistor from the same model, the beta value could change, and then you would have nonlinear distortion. So a more practical circuit is to use a voltage divider bias, also apply a resistor at the emitter. So you have 4 resistors in the circuit. We call it a 4 resistor bias circuit or a voltage divider bias circuit. That voltage divider bias circuit would take one single voltage, VCC, divided into 2 different voltages that goes into the base Again, the analysis technique remains exactly the same. We divide it into half. One side is the input, the other side is the output. Apply KVL on the input, apply KVL at the output. You obtain equations for your input base current. Your base current is the input, so you obtain expressions for IB. Okay, you obtain expression for IB, then you obtain expression for VCE and IC at the output. Well, IC is simply beta times IB, so there's not much of an, you don't have to do any derivation for that. But we do need to derive an expression for VCE, and we simply obtain that by applying KVL. So no matter what kind of circuit or what kind of amplifier you're faced with, always think in terms of Ohm's law, KVL, KCL. Those are the only three equations you need to think of. That's it. The model, the transistor model could be different. Again, in this case, we used a simplified model where we have a transistor model as a current dependent current source, right? Because the output current depends on the input current, beta IB. But everything else about the circuit is still the same. So with that, I would say we are at an end of chapter 2. There are, I think, 1 or 2 more homework assignments. There's a amplifier circuit, and then I'm trying to think if BJT had another assignment. 2 perhaps. And then I'm not debating, but I'm leaning towards assigning quiz 2 over the weekend, or quiz 3 over the weekend. But I will open it up for the entire weekend so students can take it at whatever time they choose. I'll open it up on Saturday morning at 8 o'clock, all the way up to Sunday at midnight. And so similar to quiz 2, you take it anytime. There would not be any live proctoring, but it would be based on, the quiz is going to be based on material that we have covered from the end of quiz 2 up to the end of chapter 2. Okay. And then basically that would be the entire chapter of chapter 2. And then next week we'd look at operational amplifiers. Okay, op amps. Okay, so we'll end class here today. I would bid you a good weekend. I know you will have to do work. I will have to do work. So if you have any questions, please reach out to me. Yes. No. No quiz on Monday. It'll just be the weekend. So students will have a little bit less than, not a little bit less, let's see, from 12 to 8. So if I open at 8 o'clock in the morning, you have 40 hours, and you can give the quiz anytime between those 40 hours. Okay. My guess is that most students would take it on the Sunday, but again, this is your choice when you want to take it. Just don't begin at 11:30 at Sunday night, because if you have any questions, I might be up, but will not have enough time to get those answers. So if you have questions, ask me sooner rather than later. Okay. And I will be available all weekend long. I'll be available in my office till 5 today. And then also I'm available via email, Zoom anytime. Okay. All right. So that is it for chapter 2.